Let's look at the overflow detection in case of subtraction addition. To note, like some people has this false idea that if it is an addition, it gives overflow, means it is my result is more than what I can represent within that number of bit. And similarly for the subtraction, since we are subtracting two quantities, like I cannot represent something below which I'm allowed to, right? And sometimes it is tendency to say it's an underflow error, like overflow for the addition and subtraction is underflow, which is completely wrong. Both addition subtraction suffers from overflow. Okay, underflow is completely different category of error, which we will see when we talk a little bit about this floating point operations. Okay, so underflow is related to the floating point operation. It's nothing to do with subtraction. Subtraction does not suffer from underflow. So both subtraction addition may suffer from overflow condition, where both of them in both of operation it says that my target result cannot be represented with the number of given bits. Like for 32-bit machine, it says subtraction result cannot be fit within 32-bit. It has to go for more bit. Similar for the addition result as well. So how it works? So overflow condition, if an n-bit operation result in a quantity that cannot be held within n-bit register, the condition is called overflow. Simple. For two unsigned number, only addition can create overflow, right? Because subtraction cannot. And for two signed numbers, overflow can occur with addition if both the numbers are positive or both of them are negative. And in that case, our overflow detection circuit is very simple. Okay, it is an XOR between the last or MSB stage carry out of the ripple carry addition circuit with the MSB but 1, the last but 1 stage carry out bit. Okay, circuit is very simple. XOR between two successive carry out bit from the MSB and MSB but 1, means the previous stage of the MSB. You XOR between them and that becomes your carry out B or V. Question is why? How we can come up with this simple XOR circuit and what is the theory behind it? That needs some understanding. So let's again take some example. Okay. So first of all, what we need to understand is this. Let's say we talk about the number line a little bit. So I have a number line, let's say 0 in the center. So anything this side is a positive value and anything this side is a negative value, right? So let's say I have two numbers A and B here, A and B, and I want to do summation. So as I said, subtraction is nothing but a summation, right? It's an addition process. Let's talk about two positive number, A and B, both positive number. Then my summation is somewhere here, right? That means it is not guaranteed in this case if my two operands A and B are can be represented with given number of bit. Let's say we are talking about and let's say 8-bit number, 8-bit value. Okay, 2's complement. This is important because we are dealing with common addition subtraction circuit. It assumes that we are using 2's complement form. So that means its range is 128 to 127, right? Minus 128 to 127. But anyway, let's take two values, positive side. So sum will somewhat also pushed along the positive axis. Okay, pushed along with the positive axis. And it might happen that this sum can become so big that it cannot be represented within 8-bit value, right? Then look at the others. Let's say I had both are negative. Then two negative number additions gives you much more negative number, right? Your sum is pushed towards the negative, more negative side, and that way it can become so negative that it no longer be able to represent it with 8-bit. Now how about if my A is here or B is here and let's say A is here. A is on the positive side, B is on the negative side. So what happened, your sum bit will be somewhere, probably from this graph you can say somewhere here, right? Your sum is somewhere here. Okay, so your B is a negative, A is a positive, and your sum is somewhere between A and B, right? If we add them up. So that means if I can represent successfully B in 8-bit value, 2's complement, and A in 2's complement, then value within them can be represented in a 2's complement 8-bit value. I won't have a problem, right? Similarly, let's say if A is bigger, then my sum would be somewhere in the positive side, right? Somewhere in the positive side. So if, again in this case, if I can represent B and A both in 8-bit 2's complement format, their summation should be representable within 2's complement 8-bit value. Okay. So it is only when my two operands are on the same side, either both of them are positive, okay, either both of them are positive, or both of them are negative, let's take another example, M and N, then my summation is somewhere here. So for both of this sample, like A and B both are in the positive size, my summation, it may happen, it could not be represented with the 8-bit 2's complement, or if both are in the negative side, then also their sum cannot be represented within 8-bit of 2's complement. If my operand is somewhat positive and negative combination, this sum becomes definitely representable within that many bits. Okay, so this is first understanding. Second understanding is this one. We are talking about 2's complement values, right? So if you recall the definition of positive number, it should start with leading 0. That means a number like this is not a positive number, right? It starts with a 1. A positive number which is must be positive value, must be start with 0. So we are talking about both positive, positive, okay, and see what is going on there. So positive number represented is something 0 and led by some other bits. Let's say I don't know. Let's represent with x. I don't know that values are. It doesn't matter in our understanding. XX 3, one more. And next positive number is something like that, and we're adding them. Addition operation. Now you see in this addition, this is what I will get as a CN, or in this case it's a 8-bit, right? C8. Carry out 8 stage, and this is what is carry out 7 stage, which is artifact of this 7th bit addition, x and y addition, right? So we analyze this like it is something, this C7 can be 0 or 1. That means for this guy we always be 0, we know in this situation, right? This will always be 0, C8. Only C7, depending on if it is 0, let's say it was 0, then this is something, our addition is something, result something like this, which is okay because 2 positive number addition gives me a positive number, right? Now let's say if it is 1, then what would happen? I can definitely say it is 1. Now by 2's complement form, this guy 1 SSSS is a negative. This is a negative, right? This is a negative value. So 2 positive value giving rise a negative value, it's definitely wrong, right? So what we can say about this now, let's do it in this way. So we are talking about C8 and C7 in this case, and my overflow bit combination. Okay, so for addition, what we saw that this guy will be 0. C8 is 0 always. So if it is 0, it is not overflow C7. If it is 1, C7 is 1, it's overflow, right? We know for the addition C8 cannot be 1, it will always be 0, right? By the construction of 2's complement. Now let's look at the negative, both negative. This condition, both negative. Now, both negative, let's pick up this one as the same example, but both negative means you're first leading them with 1, right? Now in this case, C8 and C7, let's look at that. C8 will always be 1, isn't it? Whether C7 is 0 or 1, it doesn't matter. 1 plus 1 is 1, 0. That it will carry out 1 in the C8 stage. So for 2 negative number addition, I have C8 as 1 always. Now let's say this guy is 0. Then what will this guy is 1. Let's start with 1. So 1 plus 1, 1, 0 plus C7 1, which is 1, 1. That means it is 1 and some, which is okay, right? 2 negative number addition, I expect a negative quantity. Fine, it is not an overflow. Now if it is 0, then this guy will be 1 plus 0, which is 1, 0, The summation becomes 0. So this is a positive number by 2's complement representation. And definitely it is wrong because two negative number addition cannot give me a positive number, right? So for this situation, negative situation, we saw that C8 should be 1 always, and if it is 0, it's an overflow C7, and if C7 is 1, it's not an overflow. And look at this. This truth table isn't it an XOR C8 XOR C7. So that's what is origin of your overflow detection circuit. In this case, we are generalizing it for an n-bit adder subtractor, and we XOR between Cn and Cn minus 1. So what our complete circuit looks like now? We have this daisy chain connected full adder, and then we have this XOR circuit controlled with the S and A bit. S and A goes to the first carry in of the LSB side of the 1-bit full adder circuit, and as an overflow detection we want to deploy one more XOR, which is XOR between C01, C2 and C3, right? Carry out 2 and carry out 3, and that becomes your overflow bit pattern, overflow bit detection for a 4-bit simplified adder subtractor circuit.